Welcome to the Shape of Space Matrix Calculus. This lesson is about functions that have a vector input and either a scalar or vector output. And in particular, we're going to talk about the gradient and the Jacobian. The gradient of a scalar valued differentiable function f with a vector input is the vector valued function nabla f. This little upside down triangle is pronounced nabla, whose value at a vector x gives the direction and the rate of fastest increase. If the gradient of a function is non-zero at an input vector or point x, the direction of the gradient is the direction in which the function increases most quickly from x, and the magnitude of the gradient is the rate of increase in that direction, i.e. the greatest absolute directional derivative. In addition, an input vector where the gradient is the zero vector is known as the stationary point. So I have a definition down here, a more precise definition. For functions from Rn, n Euclidean space, to R, the gradient is given by the partial derivatives over each input parameter. And we see here we have the nabla f of x. X is a vector. And then the gradient is on the right here. It's the partial derivative with respect to x1, x2, all the way down to xn, evaluated at the input vector x. So you get a vector, it has a direction, and it has a magnitude. I have an example in the next slide, which I'll show you. Alternately, we can express nabla f as a linear combination of the standard basis for Rn. And I show that here. So you have the partial derivative with respect to x1 times e1 and so on. Remember, e1 is just a 1 in the first position and a 0 everywhere else. e2 is a 0, a 1, and then 0 is everywhere else, and so on. We also have an example. We have a mapping f from R3 to R. So the gradient is the partial with respect to each one of the variables here. So let's do each one. So it would be 2x1, then this would just be x2, and then these don't have x1 appearing at all, so they would be 0. So we get that here. Then we take the partial with respect to x2, 0, x1, 2x2, x3, and then 0 again. Then the partial with respect to x3, this is 0, 0, 0. This would just be x2. This would be 2x3. Or we could write it in this format here. Just take this one times e1, this times e2, and this times e3. And then the stationary point, and the only stationary point is 0, 0, 0. Okay, that gives you an output of 0, 0, 0. That's the only way of getting it. Some functions have more than one zero, a stationary point, but this has just the one. So going up one level of complexity, instead of going from Rm to just R, now we're going from Rm to Rn. So we have a vector input and we have a vector output. So f of x is a function, each component of the output is a function of x. So I'm drawing it like this. So this is just f of x. So if we want to get the derivative of f at a point, it's represented by what's called the Jacobian, and it's denoted either d, capital D f of x, or j sub f of x, and it's expressed as follows. So this is the Jacobian, and you see that across the first row, you're taking your output, f1 of x, and you're doing the partial with respect to x1, x2 up to xm. Since there's m variables here. And then you take f2 and you take the partial with respect to each variable. And you get another row, and then you keep going until you get to the function nth component of the output. And then you take the partial derivative of that function with respect to each of the variables. So you get a matrix like this here. I have an example here and then a rather complicated theorem. Let's take the example first of the Jacobian. So we have a function of three variables, x1, x2, x3, and it maps to R3, so you have three components here. And the Jacobian at a point x would be the partial derivatives with respect to x1, x2, and x3 of the first term here. So you'd get 5x2, x3, and then 5x1, x3, and then 5x1, x2. Then you take the partial of this with respect to x1, x2, x3. You notice the middle term is 0 because there's no x2 in this at all, and then you get 2x1 and 2x3 for the other two. And this one's even simpler because it's only the second term here that has a non-zero partial derivative, which is 3 sub x sub 2 squared. Now, the inverse function theorem. We have a function f from Rn to Rn. It's continuously differentiable. And what this theorem says, and you have a point x in the domain such that the determinant of its Jacobian, so for example this here, does not equal 0. If you have that, then what this theorem is saying in a rather complex manner in terms of what's called topology is that there's a open set in Rn about x and an open set in Rn in the codomain about f of x, such that you have these really nice properties that f over these subsets of Rn and Rn, v and w, is a bijection. The inverse exists in between v and w, not necessarily across the whole domain and codomain, but within these subsets. The inverse not only exists, but it's continuously differentiable, and it's given by this formula here. The Jacobian of f inverse at f of x equals the Jacobian of x with respect to f and taking the inverse of that. And I will give you a reference to a proof. It's not really all that easy. It's a whole paper, and this was like the least complicated statement that I could find of the inverse function theorem for vector functions. And as I say, I'll give you a link to the paper on this topic in the information to this video.